Hello, welcome to the first video for chapter 21 on heat engines and refrigerators. So we spent a lot of time talking about theoretical aspects of thermodynamics and PV diagrams. This chapter is all about applications of this. The main applications are in engines and refrigerators. And as we'll see in later videos, this is really related to the second law of thermodynamics. All right, let's jump into it. So, oh, by the way, so we'll also talk about, in addition to introducing engines and refrigerators, we'll talk about measures of how well they perform. So for engines, we talk about the efficiency of an engine, eta. That's a Greek letter, eta. And then the coefficient of performance of a refrigerator, K. Okay, and the motivating example here is, so given some information about your car engine and how efficient it is. So this is related to the definition of efficiency. How can we relate work, so the useful thing that we get out of the car engine, with waste heat? So this chapter says that they're related. Okay, so just as a reminder, your book starts off by saying, your book's kind of funny because it says it's more useful to talk about work done by a gas rather than on the gas. It kind of admits that it should have done this from the beginning. So I just want to remind you that for notation, your book uses W, and then in this chapter they introduce something called work done by the system, and they call it WSYS. And so I'm just going to continue and keep on using this, W by, the work done by the system. Yeah, so in terms of the first law of thermodynamics, you can write it several different ways depending on whose notation you're using. So you could use delta E thermal is Q plus the work done on the gas. Your book calls this Q plus W. You could also call it Q minus the work done by the gas, and your book would call that Q minus W system. So you see the way that all of these are related. So I'm using the things on the left right here. Your book uses the ones on the right, but it's all different ways of saying the same exact thing. Okay, so engines. So we'll just talk about engines at first. So the point of an engine is to turn heat into work. That's the whole point of an engine. So wouldn't it be nice to take all the thermal energy out of an object, which is largely useless, right, and turn it into something useful? So your car engine does exactly this. You ignite the gasoline, so you get it really, really hot, and then you take that thermal energy, that hot thermal energy, and you use it to well, the energy goes from the engine to the transmission to turn your tires, and you get some useful work out of that. So we'll be talking about engines in terms of energy flow, in addition to PV diagrams. So this video will in particular talk a lot in terms of these energy diagrams, and later on we'll make the connection with PV diagrams. So the solid line right here is the system. Okay, so this is the working substance of the engine. So it might be just like a certain gas. Okay, so the goal is here to take energy from the hot thing. So any energy that flows as heat from the hot surroundings, from the hot surroundings into the system, is labeled QH. So you could think of it as hot. So or high temperature. So the goal is to turn all of that energy into work, the work output, the work done by the system. So see how energy is leaving the system, and that's why it's work done by the system and not work done on the system. So the goal here is to 100% turn all of that energy into, all of the QH thermal energy into work done by the system. It turns out, though, that that's impossible. You can't turn it 100% into work. So we'll explore why that is throughout the chapter. But suffice it to say that, there has to be, there's going to be some leftover thermal energy. And your book calls this QC. So C for cold. It's heat ejected to cold temperature surroundings. So other books will call this QL for low temperature reservoir. So the H could mean hot or high temperature. This is either C or L. C for cold or L for low temperature reservoir. So just in terms of conservation of energy, we have QH. So that's the energy that flowed into our system, has to be what flowed out. So this is work done by the gas plus whatever energy is left over as heat. QH equals W by plus QC. So this is what your book is talking about in terms of energy transfer diagrams. So if you don't fashion an engine at all, heat just normally flows from hot to cold. So you normally have this energy transfer diagram. So all of the heat that went from the high temperature reservoir, from the hot reservoir, just goes straight to the cold reservoir. So that's what normally happens. That's what happens if you don't make anything. That's just what nature naturally does. But so humans were quite clever in the 1800s and figured out that, well, we can actually use this flow and get some work out of it. So that's where this W by comes into play. Maybe we can fashion, we can get some useful energy out of this temperature difference. Okay, so you're used to diagrams like this, not like this. And this is going to be related to the fact that this engine can't be 100% efficient, but more on that later. So work into heat. So this is all about, this diagram that we just drew right here. Okay, so the book gives you a little background information, but this is what we want. Now, the measure of efficiency here, so efficiency of an engine. We use the letter eta for this. This is the efficiency of the engine. And this is defined to be, in terms of these quantities, it's defined to be, it's a number that's encapsulating how good an engine is. So we want to maximize this thing. So the ratio, the definition is going to be what we want out of this engine. So we want to maximize the numerator and minimize the denominator. So it's what we want on the top and what we have to pay for it. What we need to pay for it. So these quotes are just sort of a way of remembering what the definition is. And what we want in an engine is to maximize this thing right here. Remember, the point of the engine is to get work, get useful energy out from that thermal energy. So the thing we're trying to maximize is work done by the gas, by the system. And what we need to pay for it is this right here. The heat that we took from the high temperature reservoir. So we're going to divide this by QH, and this is the definition of efficiency. So maybe I should call this one the definition. This is just how I remember it. It's this thing right here. Okay, and notice your book also calls this W out. It's the output from the system. So the work out of the system, or the work done by the system. So there's a slight distinction because we're going to be talking about closed paths on a PV diagram. So notice on this picture, which is representing an engine, notice how the area here is positive, but we're adding up the W by for each step. So what I mean by this W by is the sum of all W bys for a cycle on a PV diagram. So your book calls this W out. So all this is to say that, so look on the left right here. If we go from point 1 to point 2 to point 3 back to point 1, that's one complete cycle for this engine. Notice how if you took the area underneath 1 to 2, there's no area underneath 2 to 3, and then the area from 3 to 1 is negative. So the net area right there is the area enclosed, so the area inside. So if you add up all the W by's for this whole thing, that will be the net work that left the system, the net energy in the form of work that left the system. Okay, so we can already, just with this understanding the energy transfers, we can start to answer this question right here. Your car engine is 30% efficient. For each kilojoule of work your car engine does, how much waste heat is exhausted by your car? So our problem says that your car is 30% efficient, which means that eta is 0.30, 30% efficient. Okay, so this is equal to the work done by the system divided by QH. Now, in the problem, we weren't told, so we were told what the work done by the engine was. We're told for every kilojoule of work your engine does, so we're going to set W by equal to 1 kilojoule. But we want to know waste heat. So the waste heat is the heat we don't really care about. It's not QH, but it's QC. QC for an engine is waste heat. Heat that's wasted. We want to minimize QC because the lower QC is, the bigger W by is, the greater work we get out of our engine, out of our system. So waste heat is QC. They're asking us in this problem to solve for QC. So we need to rearrange this efficiency formula to talk about it in terms of QC. So I'm going to use this right here to rewrite QH is equal to W by plus QC. So the problem is asking if W by is 1 kilojoule, what is QC? That's exactly what, that's rearranging the problem in terms of the equations that we've already introduced, in terms of the definition of efficiency and what waste heat is. Waste heat is QC. So rearranging this formula, we get 0.30 work by plus QC. So I just moved the denominator over to the other side, is equal to W by. It looks like 0.30 QC is equal to 0.70 times W by. So QC is 7/3 times W by. So the answer to our question is if I plug in 1 kilojoule for W by, it looks like I get 7/3 kilojoules for QC. So for every 1 kilojoule of work, there's 2.33 kilojoules of waste heat. That'll be the answer to our problem there. Okay, 7/3, 2.33. Yeah, so remember the 30% has to do with, for every, so another way of saying what that 30% means is for every 1 kilojoule taken out of the high temperature reservoir, only 30% of it goes to work. The other 70% goes to waste heat. So that's why it's this fraction 7/3. It has to do with 70% waste heat, 30% work. Okay. Okay, so your book also goes over some examples right here. Rank the work outputs. So you have to use that conservation of energy there. Now your book talks about heat engine example. So engines are designed to be used over and over again. So your car engine it goes at thousands of revolutions, thousands of cycles per minute. And so a lot of times, so representing what the engine is doing in terms of PV diagrams involves a closed cycle because you need to reuse the same gas over and over and over again. right? If we're going to do this thousands of times, we better not, deplete the source real quick. So even though there's all sorts of energy going into and out of the system right here, the substance, the working substance, the gas, described by this PV diagram remains constant. We're just changing the pressure and the volume as we add heat or take heat out of the system. So notice the flow of energy right here. So anytime, so this PV diagram on the left is the system for this picture on the right. Anytime heat goes into the system, those heats count as part of QH. So this PV diagram on the left has 3 paths. From 1 to 2, the gas is heating up. That means energy in the form of heat is being added to the system. The heat is flowing into the system. That means it came from the high temperature reservoir here. It's flowing into the system. From 2 to 3 and from 3 to 1, heat is leaving the system. And for that reason, both of those will count towards QC. Okay, so energy in the form of heat from 2 to 3 and from 3 to 1, those both, when you add them together, they both contribute to QC. Okay, and the sum of the heats don't need to be 0 for a complete cycle, which is a closed path in the PV diagram, but they're going to be related by the net work output. So that's where this formula comes in right here. So the difference in the QHs and the QCs is the area of that cycle, which is the work done by the system. Okay, so your book analyzes heat engine more quantitatively right here, but really that's the whole point of sections 3 and 4. So we'll hold off on doing this quantitative analysis for the next video. Okay, refrigerators. What color here? Refrigerators. So if we're to draw the same energy transfer diagram, maybe I'll do. So we're going to have a hot reservoir and a cold reservoir. Now the point of a fridge is to take heat out of a cold temperature reservoir. If you think of your refrigerator in your kitchen, the point of it is to take heat out of the inside, and it doesn't matter where it goes as long as it's outside of the refrigerator, right? We're trying to get it as cold as possible. So we have some working substance. This is our system, our working gas, and the point is to get energy out of the cold temperature reservoir. So maybe for energy, again, I'll use red right here. So the point is for the energy to, and this is QC, it's energy in the form of heat that came from the cold temperature reservoir. So notice how the flow of heat here, so QC, and all of these are positive quantities. So notice I'm putting the direction of the arrow, but QH is by definition the magnitude of these things. All of these things are positive. Okay. But notice how the direction is different for a refrigerator as opposed to an engine. For an engine, you're expelling, so energy in the form of heat is leaving the system going towards the cold temperature reservoir. Whereas for a refrigerator, that arrow is opposite. Now there's no way, normally heat doesn't work, normally the flow of energy doesn't work like this, right? You don't go from cold to hot. So the reason we have to induce this some way, and we have to input energy in the form of work. So instead of work done by the gas, I'll put work input. Okay, so remember I called this W by, I could also call this W out, the overall output. Maybe I'll put output right here, just to clearly distinguish it from my refrigerator and the network output. So this is the work input to the system, and then overall to conserve energy, this needs to leave the system and go towards the high temperature reservoir, the hot reservoir. Okay, so what's going on? So in order for energy in the form of heat to leave this thing, the system needs to temporarily be even colder than the cold temperature reservoir. So this is where the work comes into play. So suppose remember, you're able to contract or expand the system as much as you want. Imagine you have your hands that you can control the gas with. Imagine you expanded it so much and so quickly that you cooled it down to a temperature lower than the cold temperature reservoir. So because of that, you've now wanted the cold temperature reservoir heat to go towards the system because the system's even colder, and then you put in work to compress it, adiabatically compress it and warm it up, and then let this gas touch a high temperature reservoir, touch the room outside of the fridge, and then if the system is even warmer than the high temperature reservoir, energy in the form of heat will want to leave the system. Okay, so a fridge involves you adjusting the system to get the energy to flow this way, which normally it wouldn't want to do that. Normally it doesn't want to, heat isn't going to flow from cold to hot. So you have to put some work into the system to do this. The measure of how good a fridge is something called the coefficient of performance. So coefficient of performance of a fridge is, again, a quantity that we are going to want to maximize. So again, the way I remember this thing is what do we want to maximize for a fridge, and how are we going to pay for it? What's the thing that we want to minimize there? So coefficient of performance, we want to maximize this. Remember, the whole point of the fridge is to take heat out of the cold temperature reservoir. So we want to maximize QC. So the want is QC. And what we have to pay for it is this work going in. Ideally, we would have no work going into it, and the heat would just automatically leave the inside of our fridge. So what we have to pay for it is the work input. Now keep in mind, the inside of your fridge is not the system right here. The inside of your fridge would be like right here. It would be the cold temperature reservoir inside of fridge. So this would be the inside of the fridge. This would be your room, the kitchen. The working substance is like the freon or stuff. It's like you can imagine there's like a black box that makes your refrigerator work. Okay, that's the system right here. That's the working substance, the freon, and so instead of the gas, it might involve phase changes or something complicated. But keep in mind, the inside of the fridge is the cold temperature reservoir. It's not the system right there. Okay. So whereas the efficiency has to be between 0 and 1. So like I was saying before, there's no perfect engines. You can't get 100%. So it is less than 1 right there. The coefficient of performance, we want to maximize it. It just has to be less than infinity. So it can be bigger than 1. It turns out that there is a maximum value, but it's not 1 that bounds it. Okay, so that's the gist of the energy flow. We're going to get into more detail with how this relates to PV diagrams and how we calculate K and eta, the coefficient of performance or the efficiency of an engine, in the next couple sections.